Section 4.8 is all about right triangle trigonometry, or really triangle trigonometry, and using this in real life to solve real world problems. One of the best things you're going to have to do today is draw a picture for all of these real world scenarios. One thing that we haven't really gone over but is important is changing what's called degrees, minutes, seconds. So degrees, minutes, seconds, which is used in surveying and like longitude and latitude, from degrees, minutes, seconds to just degrees form. It loses some of its specificity, but it is what we need to be using in these problems. So the way that you do that is a conversion. Degree stays the same, and you add the minutes divided by 60 and the seconds divided by 3600. So 42 degrees, 24 minutes, 36 seconds is the same as 42.41 degrees. And 120 degrees, 1 minute, 2 seconds is the same as 120.02 degrees. There's going to be a lot of rounding in this lesson, so it doesn't really specify necessarily if you round to the nearest tenth or hundredth. When in doubt, round to the hundredth, so that's 2 decimals, but really you're rounding to the degree of an angle specified, so usually 1 or 2 decimal points. Now some vocabulary you might see in these sections has to do with angles of depression and elevation. If you notice, in the angle of depression, we are talking about the angle downward. So here is a man standing on a cliff looking at these lovely people in a boat. When we would measure the angle of depression, we're measuring from horizontal, from his eyesight, downward. That's the angle of depression, because it's going down. And when we talk about angles of elevation, we're actually talking about the eyesight of people, right? Wrong thing. Here's the eyesight of people, and the angle of elevation is them looking up from the horizontal. So that's going to be important to know the difference between angle of depression and angle of elevation in these word problems that we have. So we're going to see problems like this Bernadette Bay Lighthouse. So it says the angle of depression of a buoy from the top of the Bernadette Bay Lighthouse in New Jersey, 130 feet above the surface of the water, is 6 degrees. Find the distance from the base of the lighthouse to the buoy. So most importantly, we have to draw the correct picture. It says the angle of depression, so going down, of a buoy from the top of the lighthouse. I know this is a boat guy, but pretend it's a buoy. The angle of depression here is not this angle, but this one. So if we were to draw a picture for this, it would look something like this. Here's my lovely lighthouse and a nice little buoy on the water. We have an angle of depression of 6 degrees. Not drawn to scale, obviously. And it says that the lighthouse itself is 130 feet. So what we also know is we have this triangle created, right? This is a triangle, but this 6 degrees is over here. So this is the triangle I'm going to work with. We want to eventually know how far the distance is from the base to the lighthouse. So I've got my x value there. But really, we're looking for this x value I keep forgetting to switch to the little arrow guy, to the x value here. Okay, so we set up some trig that we know. Since we know that angle of 6 degrees, and we know that this distance has to be 130, we know the opposite of the angle. We want to find the adjacent to the angle, not the hypotenuse. We know the opposite, we want the adjacent. So tangent involves the opposite and the adjacent. So does cotangent, but we're going to use tangent here. So if we take the tangent of 6 degrees, it should be equal to the opposite over the adjacent. Well, we can quickly solve for x here and throw that in a calculator, making sure a calculator is in degrees, and get 1,236.9 feet. That's how far out the buoy is from the lighthouse. In this equation, it says from the top of a 100-foot tall Altgelt Hall, I don't know if I'm pronouncing that hall correct, on the University of Illinois campus, a man observes a car moving toward the building. The angle of depression of the car changes from 22 degrees to 46 degrees during the period of observation. How far does the car travel? Again, first things first, we need to draw a correct representation of both cars. and then label the triangles correctly. So here's my lovely drawing for this. My cars look great. Let me give them some wheels actually, so they actually look like cars. Here's my cars. And here's what's happening. There's a dude standing up here at the top of the building. Pretend like his eyesight is down at his feet. And he's looking, and the first time he sees the car, the angle of depression is 22 degrees. And as he continues to watch the car, he measures again, and the car, which is moving towards the building, is a new angle depression of 46 degrees. So we've actually created two triangles. We have this first triangle, and we have this triangle. Okay, eventually we want to know how much the car has moved. So we're going to compare the first distance to the second distance, or if I draw it in my triangle, the first distance to the second distance, and just see how much is left over when we subtract them. So I've labeled these as x1 and x2 to talk about the distance first car is, distance second car is, so we can find the change in those distances. Okay, again, just like the example before, we know the opposite, 100 feet, and the adjacent is what we want. So we're going to use tangent again, but we're going to have to use it twice because we want both the furthest distance for car 1 and the second distance when the car is at position 2. And so we do that trig. But we, again, want to know how far does the car travel. So really, we just need to subtract these two things because our distance it travels is the first one minus the second. So the distance that the car travels is 150.94 feet. We're using trig to solve problems that geometry just isn't enough. Okay, this one's cool. Okay, so like we're at a parade and the parade is moored, a parade float, sorry. This helium-filled penguin is moored, which means tied, at the beginning of the parade route. Two cables attached to the underside of the penguin make angles of 48 degrees and 40 degrees with the ground and are in the same plane as a perpendicular line from the penguin to the ground. If the cables are attached to the ground 10 feet from each other, how high above the ground is the penguin? All right, this penguin better appreciate all of this trig we're doing for it, but we're going to draw a picture to represent the situation. Please don't laugh at my penguin. Sorry, I laughed at my own penguin. Okay, here's the situation. So we've got a penguin float in the air, and it's attached by two cables. Now, the first cable makes an angle of 40 degrees with the ground. It's an angle of elevation. The second one makes an angle of 48 degrees. We know the distance between the two cables is 10 feet. We don't know the distance from the second cable to the diagonal. Sorry, that's called the straight line, not a diagonal. But we know that we want that height. We want to know how high the penguin is off the ground. So we have some very interesting trig to do here. If you notice, we have two triangles. We have this triangle that uses the 40 degrees, whose opposite side from 40 degrees is h, and whose adjacent side is 10 plus x. We also have this triangle created, whose opposite side from 48 is h, and whose adjacent side is x. Okay, so a trig measurement that involves both the opposite and the adjacent is tangent again. So we're going to set up what's called a system of equations. So we know that tangent of 40 is equal to h divided by 10 plus x. So the opposite divided by the adjacent. We know that for tangent of 48, it's the opposite divided by the adjacent. We just don't know what x is yet, but no big deal. If we have two equations, which we do, and two unknowns, which we do, we can solve. Here comes the algebra part. So the first thing that I did is I solved both equations for h. The moment that they're both solved for h, that means that they're equal to each other. So I can just set them equal to each other. I also distributed this tangent of 40 into this parentheses. So this is 10 tangent of 40 plus x tangent of 40. That's what h was equal to a second ago. So we can set it equal to x tangent of 48, which is what h is also equal to. But now my goal, my only variable left in this equation is x. So I need to start solving for x, which first of all means they should all be on the same side. So I'm going to subtract x tangent of 40 from both sides. And then I'm going to factor out x on the right-hand side. X is the greatest common factor between these two terms. So if I just, take x out, all I have left is tangent of 48 minus tangent of 40, which was right here. Okay, I'm one step away from solving for x because x is ready to be by itself. We just have to divide by tangent of 48 minus tangent of 40. This should sound familiar because we did something like this when we did logarithms. We had to solve some logarithms and exponential functions. So we can throw into our calculator that x is equal to 10 tangent of 40 divided by tangent of 48 minus tangent of 40. Making sure everything is in degrees, we'd find out that the distance x is approximately 30.90 feet. Well, that's great, but that's not actually what I care about. Remember, I care about finding h. So if we were going to plug the x value back into one of these equations, would you rather plug it into this first one or the second one? Yeah, hopefully you're saying the second one because there's less algebra to do there. So what we're going to do is we're going to plug it in. Tangent of 48 is equal to h divided by x, which we just found to be 30.90. Quickly solve for h. We get that h is equal to 30.90 times tangent of 48 degrees. And that finally, that penguin is 34.32 feet in the air. The trig is not that confusing. The algebra might be where I lost you on there. It's just the algebra. If you get a good picture drawn and labeled correctly, the trig is pretty simple. Here's where the trig is also pretty simple, but not in an example that we are used to. We live in Texas, we live in Dallas. We are not really boating folk, if you will. So this example might use some vocabulary that you're not used to. A U.S. Coast Guard patrol boat leaves Port Cleveland and averages 35 knots, which is a nautical mile per hour. Think of that as speed. Traveling for 2 hours on a course of 53 degrees. So in navigation on water, you measure everything from north, I've been told. So saying it's 50 on a course of 53 degrees means we are 53 degrees from north. Like that's going up, that's north. So 53 degrees from it. And then it's going to make a large turn and travel for 3 hours on a course of 143 degrees. So it makes a turn on a dime. Okay, 143 degrees from north again. What is the boat's bearing and distance from Port Cleveland? So when I'm asking about bearing is talking about the angle from Port Cleveland. And then the distance from Port Cleveland is just asking for this distance. Whoa, that is the ugliest line I've ever drawn. I'm just going to erase it and start over. This distance from A to C, from the beginning to the ending point. So we're going to use the picture. And then remember that distance is equal to the rate times the time. This is so important. That's a physics formula that we use a lot in math. Distance is equal to the rate or velocity times time. How fast you're going and for how long. So with that information, we should be able to figure out how far this boat went from A to B and from B to C. Because we were given the the miles per hour or nautical knots, as well as the time and the nautical knots, which is the same, and the time. Okay, so if we want to figure out this, we know that AB, the distance AB, is going to be the velocity, 35 knots, for 2 hours. So rate, time, which means it's gone 70 nautical miles. When we turned segment BC, they were going, again, 35 knots, but for 3 hours this time. So that's 105 nautical miles. And since that's one side of the triangle, two sides of the triangle, we can use good old Pythagorean theorem to find the third side of the triangle, AC. It's just good old a squared plus b squared equals c squared. So we find the first side, the second side, square them, and then take the square root of the sum. We get that it is 126.2 nautical miles from Port Cleveland. That is the distance that the boat is when we were asked to measure. That's that purple side. That's how long it is. Okay, now if we were looking for the bearing, again, remember we're looking for that theta that's on this triangle. I redrew the triangle here just to make it kind of simple, but we know all three sides, but we don't know any of the angle measurements besides this 90-degree hairpin turn, but we want this theta. So, I mean, it doesn't really matter which trig function you use. I stuck with tangent because those were given, and this one's I had to round it. So we know that the tangent of this theta is going to be the opposite, 105, divided by the adjacent, 70. And this is where the inverse functions for tangent, cosine, and sine come in handy, because we want to find out this theta. The only way to work backwards when you don't know the angle is to use the inverse tangent. So we're going to take the inverse tangent of 105 divided by 70 in our calculator. Yes, there's a button for it. It's above tangent. And then we know that the bearing, that theta, is 56.3 degrees. Now, this next couple examples are pretty cool. It's going to feel very physicsy because it really does come from physics, but we're talking about simple harmonic motion. Because of their periodic nature, sine and cosine functions are helpful in describing the motion of objects that oscillate, vibrate, or rotate. For example, the linkage here converts the rotary motion of a motor to the back and forth motion needed for some machines. When the wheel rotates, the piston moves back and forth. If the wheel rotates at a constant rate, called omega, it looks like a W, but that's the Greek letter omega, radians per second, so that's a rate there. The back and forth motion of the piston is an example of simple harmonic motion and can be modeled by an equation of the form D equals A cosine of omega t, given that omega is greater than 0. So no negative omegas, which makes sense because it's a rate. A is the radius of the wheel, and D is the directed distance from the piston at the center of oscillation, which is a whole lot of physics words to say that simple harmonic motion can either be sine if it starts at 0, or its starting position, its initial position, or D equals A cosine of omega t if it starts at the amplitude. Remember, omega is the radians per second, so it helps me know the frequency of this motion, omega divided by 2 pi. That also helps me know that the period is going to be 2 pi divided by omega, because frequency is the reciprocal of period. So all of that to say, when we're writing these equations, we need to know the amplitude, that's always been A, and we need to know the rate, or what was the B value a little bit ago, but that's now omega because we're doing harmonic motion, back and forth. So let's just see an example of simple harmonic motion. In a mechanical linkage like the one shown on the previous page, figure 4.94 in your textbook, a wheel with an 8 centimeter radius turns with an angular velocity of 8 pi radians per second. What is the frequency of the piston, and what is the distance from the starting position exactly 3.45 seconds after starting? First step is to draw this information on a unit circle so that we can figure out all of our information. So here's my unit circle. It said that I had a radius of 8. Okay, so I drew my radius of 8 here and here because this is still a radius and that's still a radius. I also know, and because it told me, I'll show you where it told me. It has an angular velocity, omega, of 8 pi. It's right there, radians per second. And A is the radius length. That's how far this piston in this mechanical linkage is moving. So my amplitude is 8. It's going to go out to 8 and back, out to 8 and back. Well, and then here. So it's going to go back and forth with an amplitude of 8, or a radius of 8. So if we're going to write the equation of this formula for this piston, since it starts out at 8, we're going to use cosine, and 8 is my amplitude, and 8 pi is the angular velocity, again, given to us. So we know the formula is d equal to 8 cosine of 8 pi t. And d, remember, stands for distance. So my first question here says, what is the frequency of the piston? Well, we had that formula from the other side that said omega divided by 2 pi is equal to 8 pi divided by 2 pi. So if we, divide, we know that there are 4 cycles per second. And if we checked this on a graph, if we graphed this function on Desmos or on your calculator, you could see that in 2 pi, there's 4 waves, 4 cycles per second. Second question says, what is the distance from the starting position exactly 3.45 seconds after starting? So we want to know, first of all, how far out the piston is at time 0. And this should make sense because it's our amplitude, but if we plug in 0 to this function for t, d of t, we have 8 cosine of 8 pi divided by, times 0, which is just 8. Cosine of 0 is 1, so 8 times 1 is 8. And then we can plug in 3.45 for t. 8 times cosine of 8 pi times 3.45, calculator tells you 2.47. So it started out at 8, and it's going back and forth, this piston is. At 3.45 seconds, it is 2.47 distance away from center, from its starting position. Sorry, not center. So if we want to figure out how far from the starting position, we're just trying to find the difference between these two values. So 8 minus 2.47 is 5.53 centimeters. Simple harmonic motion. Last but not least, if we have a mass oscillating, so this is just like an object, we're taking basically a physics experiment here. Some object, a mass, oscillating up and down on the bottom of a spring, as you can see here. So it starts here, it goes boing, boing, literally bouncing like a wave. We're going to assume perfect elasticity and no friction or air resistance. So basically this is happening in a vacuum, but we're going to model it as harmonic motion. If the weight is displaced a maximum of 5 centimeters, displacement, it's moved 5 centimeters, find the modeling equation if it takes 2 seconds to complete one cycle. First thing we need to do is choose either sine or cosine. But because this mass starts at 0, we haven't pulled the weight down yet to make it start bouncing, we're going to say that that starts at its center so that it can keep going down and go back up. So it starts at center, which means it's going to be sine. We need the amplitude. It says its maximum displacement or change is 5, so it goes down 5, up 5, down 5, up 5, over and over again. So my displacement, my a value, is 5. We need to find the period of the function so that we can write the trig function. So again, we chose sine, and all we need to do is plug in a and omega. Well, a is 5, so great, we take care of that. But how we find omega comes from this 2 seconds to complete one cycle. So we have this should say seconds per cycle. If we do seconds per cycle, we're talking about both the frequency and the period. Remember, the period is 2 pi divided by omega. That used to be b, but in angular velocity and angular momentum, that's now omega. We change what we use in physics, so we change what we use in math because math is physics. So we know that there is 2 seconds per cycle. That's the period. It takes 2 seconds to go a full cycle. And a cycle is the period. So if we have 2 pi divided by omega equal to 2, then if we solve for omega, we got pi. So the formula here is d equal to 5 times the sine of pi t, the displacement and the angular velocity.